This is the first example for electric potentials. Please read the question carefully and we'll move on to solving the problem. So before we move on, just as a quick recap, we're given this line of charge on the z-axis. There's a cylinder around it. We have the electric potential inside the cylinder given by this equation over here. We have to find K. We have to find the electric field inside the cylinder and the electric field outside the cylinder. Let's start by drawing a diagram. So here's what the coordinate system looks like. Here we have the line of charge with charge density rho L, and this is the cylinder around the line of charge with radius B. So let's do part A now. We're given this equation, we have to solve for K. Also, we know that at rho equals B, the potential is 0. That's given in the question. So when I substitute this into this equation, it's very simple to solve for K. So let's just substitute rho equals B, and I have this over here as a result, so I can easily solve for K. There you have part A done. Let's move on to the next part of the question. So in this part of the question, we have to find the electric field inside the cylinder. We're going to use this very useful piece of information. E is equal to the negative gradient operated on this V scalar. So E being the electric the electric vector field, and V being the scalar electric potential. So I'll just quickly write down a recap of what this gradient operator does. So because we're using cylindrical coordinates, this is the result of the gradient operator on V over here. And this you can find in your textbook, and you should have reviewed the theory and gone over this in math, but it's not necessary to solve the problem in this question. It is useful to know though. So this is how this works. So let's do this on the previous equation. So this is the equation. Let's use the gradient operator. This is the result from just doing the partial derivative of V with respect to rho. You get this as a result, and this should ring a bell if you've gone over electric field for an infinite line of charge. The other two derivatives will simply go to 0 because this equation does not depend on phi and z. Putting this term and this equation together, we find that E is equal to rho L over 2 pi epsilon naught rho in the a hat rho direction. So this is exactly how you might have thought it would be, because of course this is the electric field for an infinite line of charge. Now that we've done part A and B, let's move on to part C. So just as a recap of what the question was, it's to find the electric field outside the cylinder, and a useful piece of information was that the potential at rho equals B, which is that edge of the cylinder, is 0. So a lot of you intuitively might have guessed that the electric field is 0 as well. So that's a fairly simple answer, but to answer why is that electric field really 0 is a bit more complicated, as there's a bit more to think about. Now, before I actually solve this part and tell you why, I'm going to leave this as an open question for you to think about. Does the presence of a 0 potential always mean that the electric field is 0? So keep that in mind while we're solving this part C of the question, and think about that at the end of this example. So I'm going to get rid of that line of charge completely, and we'll just focus on the point charge. Here I've surrounded the point charge with this cylinder, and I've grounded it, giving it that 0 potential, just as the question had suggested. So this now begs the question of what is this 0 potential ground really mean? Well, all ground is it's just a reservoir of charge. That's a cool way to think about it. So it's just this vat of free charges just moving around. So when I have this lone point charge in here, This will attract the negative charges from this reservoir of charge to the outer surface of this cylinder. I'm going to show you what that looks like. Please take note that this is not an exact depiction of what this would look like, but just an illustration. And this point charge will keep attracting these negative charges until it can't do it anymore. That is, until the forces are balanced. And when this happens, if you take a Gaussian surface and put it around this cylinder, you'll find that the sum of these charges is 0. So your Q enclosed is 0. And what we know from Gauss's law is that Q enclosed inside the Gaussian surface is 0. The electric field out is also 0. And that is why E equals 0 outside that cylinder. Using this idea of combining Gauss's law and electric potentials and Coulomb's law, when we thought about this, answered properly why that electric field was 0 outside the cylinder. So now I want you to think about that question. Does the presence of a 0 potential always mean that the electric field is 0? And leave that for you to think about.